findings from Lab 1 surrounding the topic of constant velocity motion. As an introduction to the lab, we used two different methodologies of studying constant velocity motion where we compared the position and time data of the video that we took of an object in constant velocity motion and compared that with the position and time data that was outputted from a computational model developed with GlowScript software. The purpose of this lab was to study the concept of constant velocity motion and compare observed data with the predicted results from a computational model, and then to determine what possible factors can and have affected the results which caused them to not perfectly overlap. The central physics principles used was that of Newton's second law, which relates how forces from the surroundings affect the motion of a system, and also of how a motion of an object in motion will stay in motion unless acted upon by an outside force. From this, we're able to derive two extremely important formulas, the velocity and position update formulas, which we used throughout the lab. Here is an overview of the results and a sneak peek, which shows that the observed and predicted position versus time data nearly aligns throughout the time interval, except as time moves on, the predicted value ends up being a greater magnitude than that of the observed value. Here's a video of that we use for our experiment.
You're good. Alright.
Going into more detail for our experiment, we created the motion of constant velocity by rolling a small wooden rod down a ramp. It's important to note that the motion was only analyzed at the point where the rod started rolling solely on the flat surface in the x direction in order to analyze the motion of an object without forces acting on it. We took this video, and along with a sample measurement and a coordinate system, we were able to have track or output the following position and time data given to the right table. We then created a computational model so that we could have data that we could compare with that of our experimental data. We first had to create initial conditions where the system is denoted by a ball variable as opposed to the system being the wooden rod as previous. We set the ball's mass, which is not important because it will be canceled out when Fnet is 0. We set the position to be at the origin to match that of our experimental coordinate plane. And we set the ball's velocity to the vector negative 0.28600, which we obtained from a calculation using the first few data points from our experimental data. We then used a while loop to continuously update the ball's velocity and position every delta t seconds up until the time is equal to 4 seconds at the end of our experimental data. The first major assumption comes into play here because we set Fnet to be the vector 0, 0, 0, because in the case of constant velocity motion, the net force acting on the system should be 0. In reality, there are forces acting on the system, which will be discussed later on, and how this could affect the issues of our results. The next step is to update the ball's velocity using the velocity update formula, and the velocity will not be changing because the net force is 0. And then the ball's position is updated using the position update formula, and the position should be incremented by the same amount each time because the velocity is not changing. When we look at our results, we can see that the total magnitude of predicted movement is seen to be greater than that of the observed motion, where the system was predicted to move 0.11 meters in total in the negative x direction, while in reality it only moved 0.1 meters in the negative x direction within the 0.4 second time frame. Now, the question is, what is the source of error that could have caused this? The first explanation, and most likely, stems from the major assumption that we discussed earlier that the net force on the system was 0. In reality, there are at least two forces acting upon the system, which are friction with the surface it is rolling on, as well as air resistance. Both of these forces act against the direction of motion, which would thus decelerate the system's movement, and explains why the observed system did not travel as far as the predicted system would have expected. The second possible source of error is that our system in the observed experiment was likely not moving perfectly in the negative x direction. As it moved, it started to veer off and turn slightly, which caused some of its velocity to translate to displacement in the z direction as well as in the negative x direction, which would once again cause the observed system to not travel as far in the negative x direction as predicted. Looking at some further questions, if we were to have switched the axis of our coordinate plane, the magnitude of both velocity and position would not have changed. However, the direction of these vectors would have changed as they would have been switched from negative to positive. The beauty of Newton's second law of motion is that it allows us to predict motion based on the net overall force without worrying about the individual forces at play. Because of this, we could assume that both friction and air resistance were forces acting against the motion of our system. However, we are not able to determine what other sources might have been in play at the time.